So we're called the Taylor series, which is f of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial x minus a to the second plus on to the nth derivative of f at a over n factorial x minus a to the n. And that's the summation of k is equal to 0 to infinity of the kth derivative of f at a over k factorial x minus a to the k. So the polynomial approximation of the Taylor series would be p sub n of x is equal to f of a plus f prime of a times x minus a, all the way up until just the nth derivative of f at a over n factorial x minus a to the nth. So if we take the actual function minus the polynomial approximation, taking all the terms of the actual function from the Taylor series, and then subtracting the terms from the polynomial approximation, and then you'd be left with the nth plus 1 derivative of f at a over n plus 1 factorial times x minus a to the n plus 1, etc. So f of x minus the polynomial approximation has to be less than or equal to the n plus 1's derivative of f at a over n plus 1 factorial times x minus a to the n plus 1. So this is called the remainder, or the error, in which the approximation is to the actual function. It's the remainder written as r sub n of x, the n plus 1's derivative of f at c over n plus 1 factorial multiplied by x minus a to the n plus 1, where c is some number between x and a. This is also referred to as the Lagrange error bound by bounding the remainder, taking the absolute value of r of n of x, the absolute value of f of x minus p of x. That remainder, or that error bound, has to be less than or equal to the absolute value of the n plus 1 derivative of f at a over n plus 1 factorial times x minus a to the n plus 1. So the maximum of the absolute value of the n plus 1 derivative at some value of x over n plus 1 factorial multiplied by x minus a's absolute value to the n plus 1. So the Lagrange error bound is described as to be less than or equal to the m over n plus 1 factorial x minus a to the n plus 1, where the nth plus 1 derivative of x is less than or equal to the m, which is the maximum. So we're going to estimate the error of sine of 0.2 from the Taylor polynomial of order 4. So the polynomial of order 4 would be sine of x is equal to x minus x to the third over 3 factorial. So using that polynomial, sine of 0.2 is approximately 0.2 minus 0.2 to the third over 3 factorial, which calculating that is 0.198667. So the approximation for sine of 0.2 is 0.198667. So to get the remainder, or the Lagrange error bound, take the absolute value of r4 of x, which is the maximum of the fifth derivative of x, over 5 factorial multiplied by x to the fifth. So to get the fifth derivative, just taking the derivative of sine to get cosine, that derivative to get negative sine, derive again to get negative cosine, derive again to get sine, and the fifth derivative, which is cosine. So we're looking for the maximum of the cosine of 0.2 absolute value over 5 factorial multiplied by 0.2 to the fifth. And that's going to be the error. Since cosine of 0.2's absolute value has to be less than 1, because cosine is between negative 1 and 1, then that's going to be less than or equal to 1 over 5 factorial 0.2 to the fifth. And so the remainder is going to be less than or equal to 2.667 times 10 to the negative sixth. So the estimate happens to be correct by at least 5 decimal places, which is a pretty good approximation. So on a side note, if we look at the sine of 0.2, that was 0.198667. And if we take that approximation number and add on the error, which was the r value, that has to be bigger than or equal to 0.198667. And so to calculate sine of 0.2 plus that error, That's equal to 0.198667 plus 0.0000267. Adding those together is equal to 0.198663. So what this means is that sine of 0.2 plus the error has to be greater than 0.198667, but less than 0.198663.